Right. Hello everyone. For those of you listening online, hello to you too. It's semester 1 2017 and this is a revision seminar for Engineering Maths IIA. And I warn you now that sometimes I'm muddling through it as I go along. Having several, nearly a decade of trying to help people with Engineering Maths IIA, I'm okay now, but I've never done a course on it myself. So just be aware that sometimes you may have to stop me and go, that doesn't match what's in the lecture notes. And also sometimes you have to say, David, you've lost a minus sign, because none of us immune from that. So yes, so I'm going to start off with systems of ODEs. So yeah, a whole lot of random stuff. I'm just going to have a quick look through the notes here, which I have thank you very much, was lent to me, or given to me, depending on whether you actually get them back or not. Okay. Well, I'm going to start where I think might be the best place to start, and which is not at the beginning, because as this is a revision seminar, it's not teaching you for the first time, fingers crossed. Okay. So the idea of this is that normally with ordinary differential equations, you have one variable like t or x, and there's one quantity that's related to that, which would be your y usually. And differential equations about saying that the way that quantity changes when t changes is related to the value itself. So with systems of ODEs, there's more than one quantity changing at the same time. A classic example is when there's mixing problems in chemical engineering, where you have an amount of stuff in this barrel and an amount of stuff in this barrel, and there's like little tubes that push stuff from one to the other, and the amount of, say, salt that's dissolved in this one will change. The speed at which the amount of salt in this one changes will depend on how much salt is coming from here and how much salt is coming out from here. And so it will depend on how much salt there is right now and how much salt there is in this one. So that's the classic problem that people use. So y1's the amount here, y2 is the amount here, and the speed at which they change will be dependent on how much stuff there is in each of them. So if there's a heap here, because it's being pushed this way, this will change faster. And if there's not so much here, because it's being pushed this way, this won't change as fast. And so they'll be related to each other how much they change. And so the idea is that how much this changes will be some sort of formula based on how much is in both of them. At the moment. And how much this changes, how fast this changes will be some sort of formula y1 and y2. That's the general concept in my head of systems of ODEs. Okay? And the kinds of systems of ODEs that you guys work on are the ones where it's all constant coefficient linear. Okay, so it'll always be just numbers attached to these, and they'll be added and subtracted together. Figuring out what the formula is not something I have very much experience in, but what to do after that I can deal with. Okay, so the problem with this is that there's two functions here. There's y1 and y2, and they're related to each other. When we have ordinary differential equations with just a single function, y1 dash is just a formula based on y1 and possibly what the value of t is at the moment. But here they're related to each other, and so simultaneously we have to figure out two functions that will satisfy both of these at the same time. And that's a bit tricky, and so what we're going to do is we're going to use matrix methods to help us do it. So I need to do an example so that this makes sense. I'm just going to make one up. Let's just hope it's not too bad. Sure. Let's do that. I have unhelpfully written them so that the y1s and the y2s don't line up with each other, I'm sorry. And so if it is written that way, we're going to have to make them line up so it's a little easier to see what is going on with this. And of course my good eraser's not there. So these numbers are probably going to turn horrifying eventually, but I'm just going to run with it and see what we get. Okay, so let's see. That's the idea there. Okay, so what we're going to do is we're going to turn this into a matrix because any time when there's linear equations going on, we can turn it into a matrix. And so we're going to have a vector which contains these two quantities. And a vector which contains the y1 and the y2 over here, and then a matrix which tells us how to produce these two rows. Like that. Because the idea being that y1 dash will be 3 times y1 minus 1 times y2, and y2 dash will be 1 times y1 plus 2 times y2. Okay. So now this is even more interesting because now we have a function that is actually a vector. We have a function that's got two, it's a vector that contains a y1 and a y2, and I could think of that, all of that as a single function in its own right that also responds to t. So before I had this maybe, so t sort of causes y1 and t causes y2 to change. And now what we're going to do is we're going to say that t causes the vector y1, y2 to change. Philosophically that's one way of thinking about it. And so what people would do normally when they write this is call this bold y. On paper it's a bold y. See how it's written bold there? Whereas these y's are not bold. Well, the bold's telling me it's a vector. Okay. And so we have this now, that the bold y dash is this matrix times the bold y. And that's how it'll often be written with a letter A normally to go in that spot where the matrix is. Okay. This is kind of interesting because matrix multiplication is a linear transformation, as we saw in Maths 1b, but derivatives are also a linear transformation. Okay, if I add two functions and multiply them by scalars and do the derivative, then I could do the multiplying and adding before or after I do the derivative and it will come to the same answer. And so, in essence, what we've made here is a big linear transformation. And we're trying to figure out which functions are unchanged by this linear transformation, which is why we're so interested in eigenthings. Because eigenthings are things that don't change when you do a linear transformation on them. So we're going to make eigenfunctions today because the things that we're operating on are functions. all lots of fun. Okay, but then just if that makes you feel uncomfortable listening to that, then please ignore it. We'll just talk about something else for a while, and it'll be okay. But if that helps you understand it, then I'm happy for you. So what we need to do is we need to figure out what sorts of functions will do this. What sorts of functions is the derivative the same as multiplying by this matrix? So back in 1A and Maths 1A and Maths 1B, we said what sort of vectors is multiplying a matrix the same as multiplying by a number? Well, it's the same concept here. What sort of functions is multiplying by the matrix the same as doing the derivative? So somehow we have to figure out how to do that. And the classic trick is to pretend that is to hope that my y is some sort of constant vector times e to the something. Now you don't normally do any of this stuff, okay? You can skip all of this work usually, but I'm going to talk about it now. So we're going to suppose, also known as hope, that y is equal to some vector which I don't know. Well, I mean, technically, it's going to be equal to this. Like that. Okay, we've got this function here, which will be a multiple of e to the lambda t, and this function will be a different multiple of e to the lambda t. And the way that we normally write that is like this. Yep?
Oh, that's right, you answered it.
Yeah. I'm just pointing out that they mean the same thing. Okay? That this is just a shorthand for that. Okay? And normally your lecturer would write this vector as a bold X. Like that. Now we want to figure out what the A and the B are. And the lambda, hopefully. And so we're going to do this. Let's just watch closely what happens here. When I do the derivative of each part of this, the A is a constant, so it'll still be there because it's multiplied on. The e to the lambda t will be the same, but I'll have to multiply by the lambda, and so that'll come down. And the same with this one. And so what we're going to end up with is we're going to end up with this. You can think of it if you like, that's not a dot product, that's a multiplication, as this is a constant vector, so it will still be there afterwards, and then we do this derivative here. And that's pretty cool. So, can I call that x? Sorry. I keep forgetting what I'm doing here. I am making it up as I go along. So, like that. And so let's just sub that in. We had that y dashed was equal to matrix times y, and y dashed is x times lambda e to the lambda t, and y is x times e to the lambda t. And being numbers, this e to the lambda t, I can divide both sides by e to the lambda t and get. And lo and behold, it's exactly what we used to see when we saw the definition of eigenvalue back in Maths 1A and Maths 1B. Magic. And so really what I need to do to figure out what the lambda is the lambda is an eigenvalue of A and the x is its eigenvalue. Eigenvector. Sorry. Lambda is an that's not an m, that's an an. Lambda is an eigenvalue of A and x is its eigenvector, or any of its eigenvectors, it doesn't really matter. The other thing I know is that any multiple of x will still work. Okay, because if I just times both sides by 2, the formula will still be okay. So I don't need to worry about, I can choose any x I want as long as it's an eigenvector for that. And if your eigenvalue has more than one eigenvector, well, there's ways of dealing with that too. Okay, so that's the reasoning behind why we're going to do eigenvalues, but it looks like we can now create this process, right? So far our process, how is our process looking? So far our process is going, sorry about that. So far our process is going that y, so that's the process so far. So we rewrite the system as that. And what now we're going to have to find the eigenvalues and eigenvectors of A in order to solve our problem. That's our process so far. As I go on, I will add to this process. I will probably rewrite the process every page that I do it so that by the end there will be a full list. Okay, so that's our process so far. So what we had was that our A was 3, 1, minus 1, 2. So we need to find the eigenvalues and eigenvectors of that. Okay. Oh, your lecturer likes to do A minus lambda I. I prefer to do lambda I minus A. Won't make any difference, it'll come out the same. So to find the eigenvalues, I need to do lambda I minus A. So I do minus A and then I put the lambdas in. You may prefer doing A minus lambda I, which would be taking the matrix as it is and putting a minus lambda down the diagonal. It's up to you how you want to do it. Really hoping this is going to be something nice. Nah. And then we need to do the determinant of that. Lambda minus 3, lambda minus 2, minus... So what have we got? Lambda squared minus 2 lambda minus another 3 lambda plus 6. Yeah, that's awful. Look at that god-awful prime number just there. But that's okay. I know how to solve that. I'm going to set this equal to 0 and figure it out. Minus b plus or minus b squared minus 4ac over 2a. What's 28? So minus 3. It's beautiful. I'm so proud of myself. I guess the minus 1 in there would become an I when I square root it. And if that's not putting the fear of God into you, I don't know what is. Okay. Interesting. So it looks like I'm going to have to figure out what to do when I get a complex eigenvalues. All right, well, I'm just going to run with it, okay, and see what happens. Let's just do what the people who invented complex numbers to begin with did and went, I'm going to keep working and hope that I can make everything cancel, all the i's cancel out eventually. So, okay, so I've got these two eigenvalues, and to figure out an eigenvector, what am I going to have to do? So we've had, I plugged lambda back into the original, this equation just here. Technically we're missing a piece of this equation. To figure out the eigenvector, it's lambda I minus a x equals lambda equals 0. So I'm going to go that's what I want to solve. And so I know that I had lambda minus 3, 1 minus 1 and lambda minus 2, so we've got lambda minus 3, 1 minus 1, and lambda minus 2. Beautiful. Okay. 5 on 2 is 2.5. So I could just, that'd be minus 1/2. Hey, that's really cool, because that's like cis of pi on something, 6 or 3, one of them. Ah, cool. Look, this one's the conjugate of that one. Isn't that nice? Okay. I'm going to have to row reduce this to get an identity matrix column. So traditionally you'd put a 1 there and a 0 there, but there's nothing stopping me putting a 1 here and a 0 here. And if I have done everything right, it should be possible to, it shouldn't be possible to get to the identity. There have to be solutions to this, non-zero solutions. So if my eigenvalue is correct, I shouldn't be able to get to the identity here. So it should be true that that second row is a multiple of the first row. So I'm just going to check if that's true. I'm going to just figure out what, well, just a second. If this is a multiple of that, like if this row is a multiple of that row, then the multiple it is half plus root 3 on 2i. Because if this was a 5 here, and I expected this to be a multiple of that, then the second row should be 5 of the first row. So it should be true. I'm just going to do this, a half plus root 3 on 2i times row 1. Okay. So I'm going to get a half plus root 3 on 2 times root 3 on 2i. Oh, they're not quite conjugates. It's the real bit that's been switched. Oh well. And minus a half plus root 3 on 2i, I'm going to have to multiply them out. So what do we get? We get minus a quarter plus root 3 on 4i minus root 3 on 4i, they still cancel, and plus 3 on 4 times minus 1. Oh, look at that! These cancel. Minus a quarter minus 3/4 is minus 1. So that second, so when I multiply the top row by this number, I get the bottom row. And so the bottom row is a multiple of the first one, and so I can cancel it out by doing the correct row operation. So therefore, if I do row 1, row 2 minus a half plus 1 on root 2i times row 1, if I do that row operation, I'm going to get that. Okay, because I just figured out what this times row 1 is. And if I do row 2 minus that, I'll get 0. Beautiful. And so I end up with a pivot in this column, which means this column is a free variable. So let's call this, I don't want to use t, because we've already used t elsewhere, so I'm going to call it s. So this variable is s. Okay. So let's say that x1 is s, x2 will be, okay, so this times s plus x2 equals 0, so that's going to be like that. Beautiful. So you'll see that the pluses and minuses switch, but that always happens. If this had just been a minus a half, then it would have been x1 is s and x2 is a half s. So I have to switch the pluses and minuses. Okay, so my eigenvector has come out to be Okay, nice. All right, sure. So I suppose the other eigenvalue has an eigenvector of its own too. But there's a really neat thing about the way matrices work. If you have a real matrix and it has a non-real eigenvalue, that's not a 5, that's an S. If you have a real matrix and it has a non-real eigenvalue, then if you do the conjugate of the eigenvalue, then you get the conjugate of the eigenvector as well. So if you do get an imaginary one, you only have to do half the work. Beautiful. All right. Well, what are we going to do with this information? Ugh. I'm going to just come back to this.
Yeah, could you please repeat that? I was just about to ask you. I didn't quite. Once you started doing the eigenvector, I kind of got lost. Just because when you started doing the matrix, you made the matrix.
Yep.
Yeah, I might just be.
Here?
No, down, further down. The second last page that you just did. Once just before when you started reducing, yeah.
I'm going to do this with real numbers as well. I'm going to come back to this. But I really didn't want to miss the opportunity of trying to do this with imaginary numbers. This is what happens when you get a revision seminar where I've made the decision on the day of what I'm going to do. I'm just going to come back to this. Let's try another example, hey? I'll just pick a matrix that I know the eigenvalues of. Okay. Yes, okay. And the other one should be -4, okay. So let's have a look at this one. Okay, so the vector that has y1, y2 dash in it is the y bold y dash. And the vector that has y1 and y2 in it is this vector y. And then we have this matrix here. So to do this, we're going to have to do the eigenvalues. Like that. And we're going to need to do the determinant of this matrix. So it'll be lambda minus 2, lambda plus 1, minus 6 times minus 3, like that. So I'm going to get lambda squared minus 2 lambda, just a second, lambda squared plus 1 lambda minus 2 lambda minus 2 plus 18. Is that right?
Minus 18, isn't it?
You're totally correct. That's good because I was feeling very uncomfortable about that answer. Yes, minus 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 is minus. Beautiful. And then I'm going to have to figure out what lambdas do that. So, you can attempt to think of things that multiply to give minus 20 and add to give minus 1 in order to factorise this into two linear factors, or you can use the quadratic formula if you desire. I am going to notice that 4 and 5 go into 20, and if it was 4 and minus 5, then that would make the minus 20, and it would also, when I added them, make the minus 1 there. So it's going to be because if I expand this out, the minus 5 times 4 becomes the minus 20. The lambda times 4 and the lambda times minus 5 becomes the minus lambda. Okay, so my eigenvalues are lambda equals 5 and lambda equals minus 4. Okay. I really should have done that the first time, I'm sorry. Okay, and so I need to find the eigenvectors. When lambda equals 5, I'm going to get my lambda I minus a. That's what I need to solve. And so I'm going to sub in 5 into this matrix up here. So I'm going to get a 5 minus 2, 5 plus 1. So 3 minus 3 minus 6, 6. And already I can see just by looking, sorry guys, already I can see just by looking at it that one row is a multiple of the other row. So, yep. So if I did the right row operations, for example, if I divided the second row by 2, then they'd be exactly the same, and then I could do row 2 minus row 1. I can get to here if I do the right row operations. Let's see if... So I could do row 1 is row 1 divided by 3, row 2 is row 2 divided by 6, and then row 2 is row 2 minus row 1, no, plus row 1. Those three row operations will produce that. Here in engineering maths, if you're pretty sure, you don't have to write your row operations down. Okay, you're allowed to just skip it. This will always happen with a 2 by 2 matrix. Okay, with a 2 by 2 matrix, if your eigenvalue really is an eigenvalue, then you won't be able to produce the identity and you're going to be forced to have a row of zeros. And that happened back with my complex numbers as well. If this really is an eigenvalue, then it must be possible to make a row of zeros with the right row operation. And I was just trying to figure out what the correct row operation was. Since this was a 1, multiplying that row by whatever's here should produce the second row, and I was just checking to make sure it all worked the way it should. Some people who are very confident in their previous work will just skip all of that and go straight to here and just say, well, I'm going to be able to make a row of zeros, so I'll just put it in and not tell the reader or myself what row operation produced that row of zeros. But you have to be absolutely certain that this really is an eigenvalue if you want to do that. Okay. All right. So with this one, I haven't finished finding my eigenvalues yet, eigenvectors yet. There's a pivot here, and I'd call this S, and then we'd have x1 minus S equals 0, and therefore x1 is also S. And so my x1, x2 becomes SS. So there's my eigenvector there, because I can bring the 1 out of that and get 1, 1. Okay. And when lambda is equal to minus 4, my lambda I minus a x equals 0 becomes minus 4 minus 2. Becomes that. And those two rows are exactly the same. So I can happily just subtract one from the other to get 0, 0 on the bottom row, and maybe divide this one by minus 3. If you really want to show your row operations. The reason I haven't divided it by minus 6 to put a 1 in this position is because I didn't want to have fractions in my answer. So I've got a pivot here this time, and so the other one's my free variable. So if x1 is s, then... Sorry? Yes, it totally should. Well done. Thank you. I warned you that you should look for me losing or creating minus signs where there shouldn't be. Okay. Wouldn't it be nice if you had someone else watching you during your exam to pick those things up? It would be nice. Okay. Yes, because they've all got minuses. And so I get that x2 is actually minus 2s. So my x1, x2 becomes s minus 2s. Like that. I just have this slightest fear that I've done something wrong along the way, so I'm just going to check if that really is an eigenvector. Is that okay? The original matrix was 2, 3, 6, minus 1. And when I multiply it by 1 minus 2, I get 2 minus 6, which is minus 4, and 6, which is 8. And that totally is times by minus 4. Good. It really is an eigenvector. Okay, good. I was just a bit afraid that I was wrong, so I thought I'd just go back and check that. Tick. Okay, so what have I got now? I've got lambda equals 5 with the eigenvalue being, vector being 1, 1. And lambda equals minus 4 with the eigenvector being 1, minus 2. And what am I supposed to do with that information? I guess I'm supposed to go back to what I said earlier when I did that, and it was that y was equal to my x times e to the lambda t. That was the original hope upon which all of this working was based. And so I get two answers. I get two different answers. I've got 1, 1 e to the 5t, and also 1 minus 2 e to the minus 4t. Well, the theory of differential equations says that my solutions ought to form a subspace. And so I should be able to do any linear combination. I think they call it the superposition principle. But it's a fancy word for just, my answers should be the linear combinations of those. So my y is going to be something times this plus something times this. Does your lecturer use like a C1 and a C2 in that spot? Yes. Yeah, whatever. I like to use A and B because it reminds me of what I did in Maths 1B. And it makes me feel more comfortable because it's a bit more familiar. It's like a security blanket. So there you go. I mean, what does this even mean, right? At the moment, we're treating my y as a vector function. Okay, it takes vectors and produces vectors. But there were really two functions involved here. There was y1 and y2. So I can actually turn this all into a single vector if I really want to. So I can multiply that a in and that e to the 5t in. And that's what's really happening. Y is equal to this vector. And so if I really wanted to match what I said originally, I would say that the original y1 function is this, and the original y2 function was this. Like that. I mean, that would be the answer to the original problem of what are those two separate functions. Okay. And I guess you could possibly have some extra conditions that said what the derivatives were at specific places. So that said, wondered what they do, that told you, so what if we also had let me just pick some numbers. What if we also had that? Well then we'd be able to sub 0 in for t and see if my vector came out to 16 minus 2. So y bar of 0 would be a e to the 0 plus b e to the minus 0 and a e to the 0 minus 2b e to the minus 0, which is a plus b a minus 2b, and that's supposed to work out to 16 minus 2. And look, now I've got two equations and two unknowns which I can solve to figure out what a and b are. Or I could do it with matrices if I felt like it. If I really wanted. It's a whole different matrix again. Okay. So if I do this minus that, I'm going to get minus 3b equals minus 18, so b is 6, and therefore a plus 6 is 16, so a is 10. So this was equation 2 minus equation 1, and this was sub into number 1. Okay, so I get that actually the y1 is 10 e to the 5t plus 6 e to the minus 4t, and the y2 is 10 e to the 5t minus 2 times 6 e to the minus 4t, and that's my final answer. So if you didn't have an initial condition, you'd have to leave it like this, which is a general solution. If you have an initial condition, you can actually figure out what those a's and b's are. Which leaves us with the problem of what happens when I have complex eigenvalues. And actually there's another problem as well. So we have some what ifs. What if the lambda was 2 repeated values? So for example, what if your matrix was that? And then your lambda would be 1 and 1. Does your lecturer cover getting two repeated ones? No. Well, maybe we won't either. Let me just look it up in the great big book of everything. This is called systems, right? System of differential equations. 159. What? Where'd it go? Oh, okay. Yeah, no. Too hard. I mean, too hard for your exam. You know, not too hard for life, but okay. You can have repeated ones as long as it has two eigenvectors to go with it, which I don't know if this one does or not. No, that one doesn't. So, okay, not covered in your course. If you had a 3 by 3 matrix, it might be possible to get two of the same eigenvalue with different eigenvectors to go with them. If you did get two different eigenvectors to go with that one eigenvalue, then you could just do exactly what you normally do, vector e to the lambda t and other vector e to the lambda t, and it'll all be okay. Yes, it will. Okay. So, but it's not covered in your course. But what if lambda equals complex? So if it is complex numbers, then it's still possible to figure out an eigenvector. Because we did that. You just have to be extra sure that you're allowed to make that 0, 0. So earlier when I did that, I still did the exact same thing I usually do. I took my lambda I minus a, and I just put the the complex number in that spot. And I subtracted. Now I haven't done any row operations yet, I've just figured out what this answer is, here and here. And this bit here is me convincing myself that it's okay to create a row of zeros in this spot. So in the first one, remember I went, oh look, that bottom row is 2 times the first row. Therefore I can subtract it to make a row of zeros. And in the second one I went, that bottom row is equal to the first row, so I can just subtract it to make a row of zeros. In this one, I went, well, this bottom row has to be this times the first row. And so if I just check that that works out, yes, it is equal to that thing times the first row, and so I can subtract it to make a row of zeros. And then I do the same thing I usually do. I find the pivot, I call this S, and then over here, just to do the full version, it's this times x1 and x1 is equal to s plus x2 equals 0, because I've just left off the zeros here. And so the x2 was that. All right. And then I took that and I created a vector out of it, and that's what I've got. And I know that the other eigenvalue has to be a conjugate of the first one because it was a real matrix, and its eigenvector will be conjugate of the other eigenvector. So any i's in here will turn into, any minus i's will turn into plus i's, any minus i's, plus i's will turn into minus i's. And anything that's just real will stay the same. So now we want to know what to do with that, because this is really frustrating at the moment, because my original functions were all real numbers. You know, they were describing the mixing of things in two barrels. I'm not supposed to get imaginary answers to that. So I need to figure out what to do. So by allowing myself to have imaginary answers here, I have allowed my original functions to be functions of complex numbers. And what I need to do is somehow combine them in a way to make them functions of real numbers again. And there is a very nice and fancy trick. Okay, so the previous example I had this. What was my eigenvalue again? 5 on 2, sorry. And the eigenvector that went with it was this. Pretty sure. Yep. It was a plus. No, it wasn't. Okay. All right. That's what I had. And so I'm going to make a solution out of that. So my solution that goes with that is this. It's x times e to the lambda t. But at the moment, this is a function that is allowed to have complex numbers in it and has complex numbers in it, so if I put a real number in it, it's going to give me a complex answer. I'm just going to figure out what this is. First, I'm going to separate this e into two pieces that are multiplied together. So I'm expanding out the t. Multiplied by both of these, and then addition up in the power is multiplication down here. And the reason I've done that is because I don't know how to figure out e to an imaginary number unless it doesn't have any real numbers attached to it. So I can figure out what this is. Because e to the something times I is cos of thing times I, the cos of the thing, plus I times sine of the thing. That's the definition of what e to the something I is. All right. So this e to the 5 on 2t is a real number. It's not going to affect whether something's imaginary or not when I multiply by it. If I multiply, that real number is not going to affect whether things are imaginary, so I can just not deal with it until later. And I can multiply this vector by that stuff. Ooh, wow. I can do the top row. Again, wouldn't that be nice if in the exam you could say, this is the only bit I can do, so that's the only bit I am going to do. You'll still give me the marks, right? And then for what's in this bottom spot, I'm going to have to multiply this by that. Okay, so I just put a letter there so that I can write down here. It's a great strategy for exams if you need more space. So when I expand this out, I get half of this and half of this. And minus root 3 onto I of this. And minus root 3 on 2i squared, but I squared is minus 1, so plus root 3 on 2 of this. Alright, so that is what goes in that spot there. I do not choose to write that out as one big vector because I don't have room. Alright, here's where the magic trick happens. It hasn't happened yet, this has just been like grinding through the algebra. If I pick out the real parts of this and make them into a vector, and I pick out the imaginary parts, as in the bits that are attached to the I, but not the I itself, and make them into a vector, then they will be the two solutions I need. So the real part of this solution, alright, here we go. The e to the 5 on 2t isn't going to change whether something's real or imaginary, so it's still there. And let's look at the real part of the first coordinate. The real part of the first coordinate is that bit there. Nice. And the real part of the second coordinate is those two bits there. They don't have i's in them. And the imaginary part of y still has the 5 on 2 because that won't change whether something's real or imaginary. It's like a mad fold-in. Alright, let's look. The imaginary part of this first coordinate is that bit there. I don't need the I because I just want to pick out the bit that's attached to the I. And the imaginary part of that second coordinate is these two bits. So a half of sine root 3 on 2t and those are my two solutions. Yay! And you'll note that they're both real now because I've removed all the i's. And so I get that the actual full solution for y is something times this one and something times this one. If you were doing this properly in the exam, you'd actually write them down in those positions just here. So this bit goes there and this bit goes there. Bang! So traditionally in exams, it's not that curly. There are not so many roots and there are not so many things happening. In many exams, you won't have a real part. You'll have doopy-doo. So just as another example, just give me a second. They'll need to add to 0. No, they won't. I'm just going to have to scribble some things on another bit of paper for a second. Okay, so here's one more. I'm going to do one more imaginary one so that we've got a real handle on how this goes. Okay. My eigenvalues of A. That's what lambda I minus A is. The determinant of lambda I minus A will be this. So it's going to be lambda squared minus 1 and minus 8. Damn it! Seriously? Yeah.
We'll make A minus 2, and then it becomes plus 2. And then you get plus 8. But you have to get plus 8 until then.
Yeah, sure. I really wanted to be a whole number when I square rooted it. Okay. That's right. Okay. Nice. So the determinant of that, I just want to check something. The determinant of that is minus 1. So yeah, okay, cool. So if you ever want to make one of these up, you need these to be equal, but minus. You need that to add up to 0 and the determinant to be positive, and it'll work out fine. Okay, and so I get lambda squared plus 7 has to be 0. Lambda squared is minus 7. Lambda is plus or minus root 7. I. Sorry? Gosh, I wish I had a team of minus checkers following me around. It's like a fairy tale for, you know, Snow White and the Seven Dwarfs, like David Butler and the 7 negative checkers. Can you see, isn't that, look, there's a little, look at this distortion. Sorry. Okay, so now I'm going to find the eigenvectors. It's been a long week, and it's only Wednesday, and it's been a public holiday. So, eigenvectors, I'll do my lambda is root 7i. It's not going to be fun, but anyway. So my root 7i minus 1. That's what I've got. All right, so this one's not nearly as nice as the other one. I would like this row to be a multiple of that row. It should be if this really is an eigenvalue. I can trust that I've done my eigenvalue right and just run with what I've got and stick a couple of rows of zeros in there and it'll be nice, but I do not care to do such a thing. So I'm just going to see what happens when I multiply the top row. So just a second. If this was a 1, that wouldn't be too bad. I'm just going to do that. So I've just done row 2 divided by row 2. Sorry, divided by 2. Okay, and now my top row should be a multiple of the bottom row. And so if I multiply the bottom row by root 7i minus 1, it should come out to the right answer. So I'm just going to see what happens. So 1 times root 7i minus 1. And let's multiply these together. Root 7i, just a second. That's root 7 on 2i minus root 7 on 2i. It's looking good. Minus a half. Minus 7 on 2 minus a half. 7 on 2 is 3.5. Beautiful. It comes out to 4 as it should. Yes. So therefore, when I do this row operation, row 1 minus root 7i minus 1 lots of row 2, it will produce, well, and I'm going to switch the rows around as well. And row 1 switches with row 2. Produces that. Nice. Okay. If you're strapped for time, feel free to skip that bit, but it's on your own head if your eigenvalue really isn't 1. Okay, so there's my pivot there. I'll call this S, and x1 will have to be, okay, so x1 plus this S will be 0, and so x1 equals like that. And so I get that my eigenvector is one. Doesn't really matter where the S goes, I guess. Beautiful. So my solution is, A solution is my x times my e to the lambda t. And I'll expand that out and figure out the real bit and the imaginary bit. Okay, so the e to the something I becomes cos of the something plus I times sine of the something. And then I'm going to have to expand that out. I reckon I've just got room to fit it in that top row. No. I was thinking there might be a way to avoid expanding it out, but I don't think there is. So this times that. So minus cos root 7t. Damn it. Minus a half of I sine root 7t. And this is cos root 7t plus sine. Beautiful. If I'd been thinking clearly, I probably should have multiplied this eigenvector by 2 so that I didn't have all those fractions, but whatever. And so the real part is this. And the imaginary part is this. And so my final solution is, well, A of this plus B of this. So I've been a bit confusing there because this y is a particular y, so I should probably stick some p's on there to distinguish it from the final solution. It's technically a particular solution. To the homogeneous one. Yay! There you go. If we were really lucky, there would have been a whole lot less going on there, but there isn't. The example in the lecture notes ended up with the eigenvector just having an I in it rather than a 1 plus root 7i. So it was even easier to do it than that. Wow, that took a lot longer than I was expecting. But it just goes to show how so many people emailed me saying, and not just in this course, but also in the differential equations course over in the maths degree, why so many people emailed me saying, can you talk me through the systems of differential equations? All right. I think I'm going to leave it at that, unless someone has another question to ask, which is perfectly okay. All right. Well, that's the most comprehensive thing on systems of ODEs I've ever done. I'll probably still keep the other one there because it's not bad to have more and more examples. Okay. What else was on my list? I've got all these whisperings with lots of S's in them, so I presume they mean statistics. And several people over the last several weeks, I have sort of half promised that I would talk about statistics, so I should, really. Okay. But to do that, I'm going to need lecture notes that talk about statistics. Oh, this does too. Good. Okay. Thank you. Well, let me just start with this. What do people want to know about statistics? Sorry? How to pass. Yes, if it was that simple, then I wouldn't have so many people coming to talk to me about their replacement exams. I'm sorry, that wasn't meant to be a burn, it was more... I wish I could make it that simple, really, because it shouldn't be as hard. It's the worst thing when you look at something and you go, well, it doesn't seem that hard when I look at each bit individually, but when I come to do the exam, somehow I still don't pass, and that's an awful feeling. And I don't like people to have that feeling. I only ever had that feeling when I was doing physics. I still just passed, but I stopped doing physics in first year and decided to do maths instead. Other people feel differently about that, and it's more the other way around. Okay. So as far as I can tell, there's like four main bits. There's, see if I can write them down. There's probability at its most fundamental level. There's distributions, which is still probability. there's various hypothesis tests and confidence intervals. And then there's regression. And these two sort of go together and these two sort of go together. Does that seem like everything? Seems like everything. I have to say it's really hard looking at your lecture slides to have a good feeling of what's there and what's not there, and where one thing ends and the next thing begins. Sorry? So one thing I would suggest is to make something for yourself that's easier to tell where one thing ends and the next thing begins. Okay. The most people have asked me about regression. So despite the fact that it's at the end, I'm going to do it first. I should warn you as well, I've booked this room all day. So if you're happy to stay, I'll just keep talking. I said it would go for 2 hours, but you know, if you have to go somewhere, it's still going to be recorded. But if you don't, I'm just going to keep going, okay? Might as well do this properly. I do have a very important question to ask about 2017, which is, has your lecturer said there will be some sort of formula sheet for statistics? Has your lecturer provided you with what this formula sheet is? Does someone have that? Oh, look and see if you can find one. Yes. Thank you. So, just want to make sure, because I don't know, I do not know the answer to this question, because I wasn't there, and I can't ask your lecturer because he's in, I don't know where he is, Europe or something. So, this is a formula sheet from a past exam. Has your lecturer confirmed that it will be the same one this year?
I believe that's the formula sheet from the sample exams that you've been given.
Okay.
I believe I'm not 100% on it, but I think that he said that that's what we're going to get exams.
Okay.
So that's the only formula sheet we've been given of any sort.
Okay.
So,
Well, my instinct is that lecturers doing a course for the first time are unlikely to change things from the past, so it seems reasonable that it would be the truth, but I can't confirm or deny that. And technically, even if I did know, I'm not supposed to. I'm supposed to tell you to check your own course. But we're going to run with this. This is a lot of stuff. Okay. Do you mind if I draw on this? Okay. In colour? Okay, good. I won't do it in text because it'll bleed through to the other side, so I'll do it in pencil. Okay, so I mentioned 4 parts of the course. Let's colour code them before I get into actually talking about regression. So we have probability is going to be pink. Distribution is going to be orange. Hypothesis test is going to be green. All right, let's have a look. Let's look for... Okay, so none of this is about general probability. You know, all those things with intersections and Bayes' law, none of that is here. So the moral of that tale is that if you need to know about Bayes' theorem, I don't know if you do, but if you need to know about Bayes' theorem, and if you need to know about intersections and stuff like that, it's not on it's not on here. You're going to have to remember that. Okay? Well, these are all distributions. Okay? And so that section there is all about different probability distributions. They all belong to the same part of the course. And these are all hypothesis tests and confidence intervals. Oh, except down to there. Not there. And these three, since they say regression, are about regression. All right, cool. So I've now separated your formula sheet into the three parts of the course that your formula sheet is about. All right. Okay. So we're going to talk about regression first, but I just wanted to find the parts of the formula sheet that were about regression. Okay. Right. Well, every statistical procedure is designed to answer a certain kind of question. Sometimes multiple questions simultaneously. So we want to figure out what questions regression answers. And we also need to talk about what kind of variables are involved. So every statistical procedure is about certain kinds of variables, whether probability or hypothesis tests or confidence intervals or regression. They're all about certain kinds of variables, and different ones work on different variables. And so I need to know what type of variables are involved in regression and what type of question regression answers. And regression is able to answer multiple questions. So at the heart of all statistics is an attempt to predict and or control variability, which is why it's used so much in things like engineering, where you have a lot of quality control procedures. And so in regression, the idea is that you have some sort of numerical variable, which I draw like this, which I'm going to call the outcome. You see, even the kids are scared. So, which I call the outcome. And different objects will have different measurements for this outcome. So, for example, it might be the angle through which Barbie's articulated knee is able to turn, for example, or it could be the concentration of a certain chemical in your thing that you're making, or it could be the weight of the actual weight of sugar inside your tub of ice cream. Any number of things that you could measure in order to help you help you decide about, usually in engineering, whether the thing that you're trying to make is doing the thing it's supposed to do. Okay, and what you want is to be able to predict what that outcome is going to be based on some other variable. Okay. Yep. Okay. You don't do multiple regression in this course, so I just was checking that. So the idea is that outcome, you could measure it and you go, okay, look, there's some variation, you know, on average they're this, and they're, you know, they can be up this far and down this far, but it may be that there's some other variable which tells you about the changes in this. And it's usually called an explanatory variable because it explains why that variable is different. So it may be that you pick two different ice creams, and the reason they have different amounts of sugar is something to do with I don't know, the temperature at which you mix the thing because the yeast ate the sugar or something. Or whatever. It could be to do with a chemical process. You might have some chemical concentration of something, and that could be completely explained by some other chemical that you put into the mixture as well. So the idea is that every object has these two measurements on it. And this is how I think about it. There is an object of some sort, and it has two things measured on it. It has an explanatory variable which is some sort of number, and an outcome, which is some sort of number. Every object has those two things measured on it. And your data will reflect that. So your data will have something like object number 1 has this number for the explanatory variable and this number for the outcome. And object number 2 has this number for the explanatory variable and this number for the outcome. And object number 3 has this number for the explanatory variable and this number for the outcome, and so on. That's what the data would look like if it was in a spreadsheet. All of this thinking helps me to figure out what's happening in any statistical procedure, and for me, regression is about this information. Okay. I should say that while you're interested in this causing that, regression does not tell you about whether things cause things, it just tells you about whether they're numerically related. Statistics cannot tell you whether anything causes anything else. That's what proper experimental design is for. Okay, so this is the setup of the data. And the other thing we need to know about a statistical procedure in order to know what it's doing is what sorts of questions it answers. So the first and most fundamental question that regression answers is, what is the formula for how this is related to that? That's the first question that regression is designed to do. In fact, that is the main purpose of regression. Maybe I should say purpose here. So I don't just want to know whether they're related, I want to know what's the formula. If I have this, can I calculate what this is? But you may also have a separate question, which is, is there a relationship? Which is a sort of a bit more of a basic question, and regression can help you answer that too. And you may have a third question of, you may, instead of needing to know the formula for all possible explanatory variables, you may want to know, given a specific value of the explanatory variable, what happens to the outcome there. What is the average outcome? All right. And you may also ask, given this value of the explanatory variable, that's not a t, what are the possibilities for the outcome? These are all sorts of questions that you can ask about this situation. And each question has a different answer. Actually, there's even one more question for this, which is, if I change the explanatory variable by 1, how much would does the outcome change? All of these are questions that you could ask about this. Now this thing here, if I change the explanatory variable by 1, how much the outcome changes, is essentially the same as asking what's the formula. But they're all pitched a different way. And each one of those, the regression output that your computer produces when you ask it to do regression, tells you different answers of those questions. And all of those questions that you could ask about your research, regression helps you to answer. Though this is the sort of the actual main purpose. But all the other ones are there. Cool. So, here we go. This what's the formula question can be done no matter what your data looks like. As long as it looks roughly straight, this one will be fine. All of the rest of these can only be answered if you know something about the distribution of the data. And so you need to check things in order to tell if you're allowed to do any of this stuff. Because figuring out what the average outcome is, or even figuring out what the possibilities for a particular outcome are really based on the assumption that you know how those outcomes are spread out. And so you need to know something about the distribution in order to do that. So there's all these things you're supposed to check in order to do the procedures that are involved in these. We'll get to them. So, how do we answer all of these questions? Well, here we go. What's the formula is answered by the regression equation. And you're just going to find in your notes oh damn it, correlation as well. This is going to be a bit small to read, unfortunately. Damn it. Okay, so the regression equation answers this, and it goes like this. I don't know if your lecturer puts a hat on it or not. Statistics is taught in a different dialect in every discipline. Oh, wow, your lecturer talks about it in a completely different way. All right. Your lecturer talks about it like this. So technically it's just this bit that's the regression equation. Okay. Yeah, I'll just leave that there. Okay, so what this allows me to do is it says that given a value of x, as long as I know what these numbers are, I can calculate what I think the y should be on average. Okay? And so I believe in MATLAB, when you do a regression, it produces a little object called beta. In which it contains these two numbers. So in MATLAB, would have some numbers in it, which would be the answer for beta 0 and beta 1. I think there's a technical detail here, is that this is the original model. Oh, damn it. This is the original model, and I think they change them to little b's when you figure out what they are in your data. Oh, no, they don't. This is my curse. You know, for my sins, I have to help everyone in the whole university do statistics, and everyone uses different notation in every discipline. And there's a course with statistics like in every degree, and they're all different. All right. Okay. This is the model, and the regression equation has hats on it. So the hat is there to say, it's not necessarily the real beta naught that works for all possible of these objects. It's just the one that I think is that I've calculated from my sample. It's the estimate. All right. And that's pretty much all that's for. You know, It allows you to calculate what you think the predicted y is for every given x, and it's the equation of the line on the graph, or graph if you like. So when you draw a scatter plot of all of your data, that's the equation of the line. And it is, in a very literal sense, the line that is closest to your points. Yep?
Why did you get rid of the E again?
So the difference... Yeah, I know, I was getting a bit confused. The idea is that you're saying, how does the universe calculate what y is? Okay? So it says that y is going to be some number plus something times the x value and a bit. And they put these little eyes on here to say it's whichever y I'm up to. So object number 1, y1 will be beta 0 plus beta 1 times x1 and a bit. And object number 2, y2 will be beta 0 plus beta 1 times x2 and a bit. And that'll be e2. So this is how the universe calculates, well, philosophically, this is how we imagine the universe calculates the value of y. It says, oh yes, I'm going to do this bit, and then I'm going to, just to stuff with you, put a bit of randomness in there. Okay? Right. But you don't know, you'll never know in advance what this is. You'll never be able to do that random part. But we can do this bit. And so then we're going to say that what I predict the y to be will be what I calculate this to be from my sample, what I calculate this to be from my sample, and whatever the x is that goes with it. Because I can't put this random bit in and and really know if it's going to be true or not. So it's a little bit like a function, only a crappy one. So you could play this game, which I play with high school students, where I have a function in my head, and it's a linear function, and you have to guess what it is. And so you'll give me a number, and then I'll give you the answer. You give me an x, and I'll give you the y that goes with it. And so, you might say 1, and I'll say 3, and then you might say 2, and I'll say 5, and then you might say 3, and I'll say 7, and you're going, okay, it's going up by 2 every time, that's the slope, and the original one is whatever it is. But with this, it's like you say 1 and I say 3.2, and you say 2 and I say 4.8, and then you say 1 again, and this time I say 3.1. Okay, so there's this random bit that affects what the formula is. And I need to somehow figure out, based on that random bit, what the original formula, line formula is, even taking into account those little random bits. Okay, and luckily, Fisher, back in the day, using multi-dimensional linear algebra and calculus, figured out that there's a formula for what these things are. Magic. And he refused to explain how he did it because he thought it was obvious. And the tradition... No, I'm not going to say that. No, I will. And the tradition in statistics teaching has continued to this day. No. Ben's a really good lecturer. If you watch this, Ben, you see, note that I said that. Okay, so that's the philosophy of it. So the next question is there a relationship? Okay, it's all well and good for me to calculate a formula, but what if there's so much randomness going on that I just can't tell what the formula really is? And I go, well, there's so much randomness, there's not really a relationship, it's totally, almost completely random. That E is just so much bigger than everything else that who cares? There's no point in me trying to figure out what the formula is. So the only way for me to answer that is to turn this into a different question. So statistics, if you ask a yes or no question, that is what a p-value is for. You did p-values in this course, right? Good. Okay, a p-value is designed to help you answer the question, a yes or no question. And this is a yes or no question. Is there a relationship? So to answer this question, it must be possible for me to find a p-value. And in order to find a p-value, I need to pick a single number that represents how close to yes or no for this question I am, and be able to figure out a probability of that value. That's like a test statistic. So I'm going to need to make a test statistic, I'm going to need to know what its distribution is, and I'm going to have to look up that distribution, look up that value in the distribution and figure out a probability. That's how you answer a yes or no question in statistics. And that's this row here in your table. This row here is designed to help you answer the question of, is there a relationship? Okay, so to answer this question, I'm going to need a p-value. I'm going to need a test statistic and a p-value. And first, the only way for me to make a test statistic and a p-value is to turn my question of is there a relationship into a question about a specific number. All of your hypothesis tests here, when they talk about the parameter, your real question might be, is there a relationship or is there a difference? You need to turn into a stats question, which is this parameter equal to something? So I need to do that too. So I have to turn the question into, is beta 1 equal to 0? Because if beta 1 was equal to 0, then my equation would be this. And it would just be some number and a random bit. And so the value of y would just be completely random, and it wouldn't be related to x at all. So the question of is there a relationship between my y and my x is the same as the question of is beta naught equal to 0. Which is why this row here, regression slope, not beta naught, beta 1, regression slope beta 1 is the thing that we're interested in. This is my estimate of what beta 1 is. And I can create a t statistic by going estimate minus what I think it is divided by standard error. So I can do this. I can go, my test statistic is my estimate minus what I'm asking about whether it's equal to divided by the standard error. According to my table. And then I'm going to look that up, what I get in my t distribution with n minus 2 degrees of freedom, and figure out a p-value, and my p-value will help me answer the question. And if the p-value is below whatever cutoff my lecturer has chosen, maybe they say I have to use the 5% level, my p-value is below 5%, magic! Yes, there is a relationship. Because p-value being low, the p-value is, Ben, I hope you're not listening because you'll slap me. The p-value is how strongly you believe in this equality here. It's not really, but close enough. Okay, we can say that in our heads, we're just not allowed to say it aloud. Okay, so how strongly do we believe that beta 1 is equal to 0? That's the p-value, and if the p-value gets too small, then I don't believe it after all. Okay. I don't have any examples to run off with that, I'm sorry, but that's the philosophy of how that works. Yep?
Values like SC and SXX there, are they going to be given in the question?
So the question for the recording was values like this SE and this SXX, are they going to be given to you? In an exam, yes. Because they're calculated by doing a standard deviation of like 50 values. So my instinct is that your lecturer will tell you some MATLAB output, and you will read that information from the MATLAB output. Or they'll give you a table with a lot of information, some of which isn't necessarily directly relevant. You need to pick out the bits you need. Okay. Of course, this beta 1 hat, it says SXY on SXX, but that beta 1 hat is from the MATLAB It's in the beta vector. Okay. All right. The next question is, given that this value of the explanatory variable, what is the average outcome? You can have that back now. So, given a value for the x, what's the average y? X for explanatory, y because it comes after x. Okay? Now, when a statistician asks the question of what is the value of this number, and they're not caring about your sample per se, they're caring about all possible objects, then they always answer that question with a confidence interval. Of some sort. Sometimes it's called a prediction interval. Today, this is a confidence interval. And the reason it's a confidence interval is I am interested in a specific single number that represents the entire group. So this average y represents a group of objects, or people, or whatever they are. In engineering, they're rarely people. Over in medicine, who I also teach, they're almost always people, though sometimes petri dishes. Okay, so because this represents a group of objects, that's why we need to do a confidence interval. I have a question. Did Ben talk about all this sort of thing? About choosing how to tell whether it's a confidence interval or not? About which questions go with which things? Good, he should. I taught him how to do that. But, okay, so given a value for x, what is the average y? I need a confidence interval, and it's a confidence, oh look, regression confidence interval. That's how I do it. And to make a confidence interval, I use the same information that I use to make a hypothesis test, but I arrange it differently. In a hypothesis test, I go estimate minus what the parameter, I think the parameter is, divided by the standard error. To make a confidence interval, I do that backwards. I take, well, no, divided by the test statistic, you go estimate minus what the parameter I think it is divided by the standard error equals the test statistic. For a confidence interval, you do that backwards. Test statistic times this plus this equals what the parameter is. So you work in one direction or the other. So to do a confidence interval, I will say that the endpoints of the confidence interval equals the estimate plus the test statistic, like the critical value of the test statistic, times the standard error. That's always how it goes, or at least in these ones. Some very fancy statistical methods that do confidence intervals don't follow that pattern, but that's because they're not going to get into that. So the estimate in our case is what I think it is at that point. Okay, so the specific x is called x naught. Just so you know, the specific x that I'm interested in is x naught. For no good reason, then I had to pick one and it's an x, and I don't know, could have called it x1, but I think that would have been confusing. Oh, that's why. Your data has an x1 and an x2 and an x3 and an x4 and a whatever. I need to pick an x that isn't in the list. It's x naught. Perfect. Yay, that's why. 0 is a handy number that I haven't used in my data already. Beautiful. So that's the estimate according to the table. Just there. And the test statistic is a t. You normally call it a star because it's not really the test statistic. It's what the test statistic would have been in order for you to reject the null hypothesis. And the standard error in this case, according to the table, is that. Okay, sure. So you'd have to know what all of those numbers were. So if I had an example, I'm going to have to pick a number for that. It's usually a big number. And all right. Suppose this was what I got from my data. Okay? And I'm interested in, you know, what's the mean y when x is, I don't know, 12? No good reason, I'm just picking something. Okay, so to answer that I would do a confidence interval. So the endpoints are, actually just figure out what all these bits are. So y hat is beta naught hat plus beta 1 hat x naught, which is 1.8 plus 2.3 times 12. You guys have graphics calculators? No. Good. I'll use a plain calculator. Which is 29.4. So that's this bit. That's my y hat. I should just while I'm at it, stick that there. My t star, well that says that it says here that it's from the n minus 2 t distribution. Oh crap, I haven't figured out how wide this confidence interval is, so I'm just going to do calculate with 95% confidence interval. I'm going to have to look that up. How does the lecturer normally deal with this in an exam question? Have you seen any past ones? Did they give you a list of t's? I reckon they'll give you a list of specific values for the t distribution. I'm just going to get my great big book of everything. Normal distribution. T distribution. This looks good. Phase is f a given phase of the distribution function. Okay, so just a second, I'm just going to need to draw a picture. So I need it to be that it's 95% in the middle, which means because it's symmetrical I'm going to need 2.5% on either side, and that's my t star just there. So oh, good. Oh. And this is the t distribution with n minus 2. Okay, 30 minus 2 is 28. Okay, so I'm going to look up my table. There's number 28. I'm going to need 0.975 because My table tells me this bit. That's the way it works. And so that's 2.05. There we go. Now, I have no idea, I'm sorry, what your lecturer is going to do. I have a feeling they're likely to just say T star for 95% confidence with 28 is equal to this. I don't know. Sorry? The MATLAB output? How did you get this in MATLAB? Sorry? It's not t-test. Oh, can your MATLAB output produce the entire confidence interval for you? T dot in? Is it a dot or is it just a... I don't know. Yeah. I have a feeling that it's likely to ask for this whole block here, everything to the left. So it's probably going to, you're likely to put in the 0.975 and the degrees of freedom. Something like that.
I'll tell you what's the value for that. Then you use that value to calculate the confidence interval.
Okay. All right. Beautiful. Okay, good. It's nice to know what's going on in this course. I should say it's not a Z. It's a T. Most things are T's. Zs are really rare. Okay. Z is the normal distribution. Whereas the T distribution's a little bit off to account for how much data you've got. A Z distribution would be if you had perfect information about the standard deviation. And if you had that, yeah, and if you had perfect information about the standard deviation, why would you be doing this? Okay. All right. And then, oh crap, I didn't put the SE in. Pick a number, guys, for the SE. Because it's never going to be a whole number. Okay. So, my standard error, according to the formula, is SE root 1 on n plus x naught minus x bar squared on SXX. So the SE was 3.1, the n was 30, the x naught was 12, and the SXX was 115.8. Oh yeah, SE is the standard error for the confidence interval when it's in capitals. The S little e is the standard deviation of the residuals. I believe this here is called mean square error in most data. Yep. The SXX is, so see how you've got x naught minus x bar squared? If you do that calculation for every piece of the data, x1 minus x bar squared and x2 minus x bar squared and x3 minus x bar squared, and then you add them all up, that's what this is. So it's the sum, that's what the S stands for, of the difference between the x's. Actually, it's the sum of the distance from x to its mean times the difference from x to its mean. Sxy is the sum of the distances between x to the mean times the distance from y to the mean. So if you actually wanted to calculate the Sxx by yourself, you would need to take whatever vector in MATLAB the x variables are in and do this. Just a second. Interlude. So perhaps your x is where your data for your x's is. That's your vector of x values. What you'll do is you'll need to figure out what the mean of x is first. Is there a function that does the mean of x all by itself? It's in the notes somewhere. You'll need to figure out what the mean is. And then your SXX will be the sum. I think sum is a thing in MATLAB. Of x minus x bar squared, like that. You need a little dot before the power so that it does the power on every entry separately, because that's the way MATLAB works. In MATLAB, if you don't put a dot there, it'll attempt to square it as a matrix, and it's going to chuck a spaz because it's not a matrix. So I'd put a dot there next to the -2 just in case. That should work to figure out what SXX is. I don't know if your exam's going to need that, but what it may give you, it hasn't been, not unknown in the past, is some MATLAB code and its results. So you need to be able to look in there to see which bit is calculating the SXX. Okay, and so this comes out to a number, whatever that is, 3.1 times the square root of 1 on 30 plus 12 minus 10.5 squared. And so finally, my endpoints of my confidence interval are going to be my 29.4 plus or minus my 2.05 times the 0.712. Because they're all the numbers I've just calculated. It's the estimate, which was the y bar, plus or minus the t, which is the 2.05, times the capital SE, the standard error. So 29.4. You should probably give yourself a few more decimal places when you do this. So they're the endpoints of my confidence interval. One of them I did the minus, the other one I did the plus. And so that means that my confidence interval itself is that. I apologise with the about the MATLAB. Maths Learning Centre is not a software learning centre. I wish it were for your sake, but I don't know enough about MATLAB to be able to just know it off the top of my head. I'm the sort of person with MATLAB who will just keep trying stuff until it works. Just my general approach to computers. It's one of the reasons I know so much about how Excel works, because I've had 20 years of just trying to make Excel do stuff. Okay. Though to be fair, I did do Excel in Scientific Computing 1. Yeah. Right. That's how you do a confidence interval if you need to do it by hand. I'm pretty sure that you can coach that MATLAB with the right instructions will just do that for you. A sophisticated computer program that's deliberately designed to do statistics will usually calculate those confidence intervals for you. MATLAB doesn't seem to, but I'm sure there's like an add-on that you could add, but not for your course. Okay, next question that we want to answer is, given this value of x, what are the possibilities for what y could be? So you'll see that's subtly different from the other one. The other one was, given the value of x, what do I think the average y is? This one is, given the value of x, what are the possibilities for y? For all the values that y could be. Okay? So the difference is, given this value of x, where'd my purple one go? Right, that's where the average y is, I think. And see all these spreads around here? These are what all the values of y could be. And that's what it is in my sample. And what I want to do is think, just a second, this is just a sample out of all possible data that there could possibly be. Where is the real average y? My data, the average y is here. Where's the real one? And that's what the confidence interval is. The prediction interval is trying to get a handle on where all the dots could possibly be. And that's why the prediction interval is wider. It's trying to cover all the possible values of y for an individual object, rather than just the average value of y for a group of objects. So this is about which means it's a prediction interval. I wish we spent more time doing prediction intervals not in the context of regression. It would make more sense, but we don't. So the difference is that your question needs to be about individual objects to be a prediction interval, and it's about the average when it's a confidence interval. And that may be hidden in the way the question is worded. Okay? So according to your thing, the prediction interval is here. See, PI for prediction interval. And you'll see that the estimate, the thing we're trying to predict is the actual value of y. It's got a 0 because it belongs with x0. The estimate is the same. The t is the same. And this is the same, except it's got an extra +1 inside it. So the endpoint of the prediction interval is Tn minus 2 star, because it's the one I chose rather than the one that came from my data. The standard error from the data, 1 root 1 over 1 plus 1 over n plus x naught minus x bar squared on sxx. And this y bar here is beta naught hat plus beta 1 hat x naught. All right. And it's a bit wider than the confidence interval. So classic thing that lecturers in other courses do is they give you a table that has prediction intervals and confidence intervals next to each other, and you can go, oh, these ones are wider, they must be the prediction intervals. Even if they've labelled them badly, you can tell which is which, because the prediction intervals, the prediction interval, these two numbers that we calculated here will be further apart. Always wider than the matching confidence interval because it's trying to cover all the possibilities for y, not just the average. Okay. What was the last question? Oh yeah. How much does y change when x changes by 1? that is a question about a specific number, and it's about a question in the real world, not in my data. And so it's a confidence interval as well. And the amount that y changes when x changes by 1, that's totally the slope of a line. So this is the confidence interval for the slope. And so I'll go looking and say, aha, look, I can make confidence intervals out of this table as well. So the CI for slope, the endpoints are the beta 1 hat plus or minus the t star SE on root SXX. All I've done is I've copied the formula from here. When you make a confidence interval, it's estimate plus or minus reference distribution times standard error. I use those same pieces to make my hypothesis test. So in that situation I had before, I can actually calculate this. My beta 1 hat was where'd they go? Oh, there it is. My beta 1 hat was 2.3. My t star n minus 2 was 2.05. And my SE over root SXX was 3.1 over 115.8. And so I can do my confidence interval for the slope. I totally do. Well done. Always nice to... You can tell I'm getting tired. And so the 95% confidence interval endpoints are 2.3 plus or minus 2.05 times 0.289. And so my confidence interval will be two numbers. There you go. So this is saying that when the x changes by 1, the y changes between 2.21 and 3.39 on average. Oh crap, you're supposed to start that sentence with, we're 95% confident that. There we go. That's regression, which took longer than I hoped. Wow. Okay, so the key thing about the way Engineering Maths IIA works, and indeed most first statistics courses in any degree, because you didn't do any statistics last year, this is your first statistics course, is that your lecturer is expecting you most of the time to run on a stimulus-response sort of basis. That you see something and you respond in a certain way. I see something that says calculate a confidence interval and I respond by looking up the formula and doing it. Okay? So in essence they want you to be MATLAB. Okay? The only difference between you and MATLAB is that you can choose what to do in any given situation, whereas MATLAB can't. So the difference between you and just asking a computer to do this exam for you is that you have to choose what to do. So they want you to be able to hone your response to the stimuli so that it matches correctly. And my way of doing that with regression is to focus on the question I'm trying to answer. Okay, questions about specific numbers are confidence intervals. Specific numbers in the population are confidence intervals. Questions about whether yes or no questions are about hypothesis tests. Questions about specific numbers for individuals are what prediction intervals are for. So I can use that sort of strategy to help me decide what to do. Actually understanding all the whys and wherefores is a different skill and is useful sometimes, but in the end you'll still have to use the information you have to make a decision of what to do. And it's a separate skill, and so it's important to learn it as a skill of its own. The only other thing is the technical details, the batteries not included that are off. You know, this whole thing of regression comes with a warning. It only works properly if the data is right. That looks way too much like a sunflower, which makes it happier rather than like a flashing warning light. Okay, this bit here in my head is like the big warning. It's like when you buy a toy and it has star, batteries not included, or star also requires the Barbie camper van. So I have to say this. I saw on the shelf on the weekend a new Barbie. I have daughters, by the way. A new Barbie that you buy a dog, and it's Barbie walking the dog, and she's got this little pooper scooper, and you actually have little poos that actually come out of the dog's bottom. So bad. Like, what were they doing in the meeting where someone suggested this and then someone said, yeah, that's a great idea. Don't. Anyway, several engineers were paid a lot to make that work, so... Okay, so warning, only works properly if the data's right. This is my big batteries not included idea. And so we need to check some things, and there are specific ways of checking them. And there are four assumptions, I think. Let's see if I can get them right. So your lecturer has said you've got to look at all these graphs to check the assumptions, right? That's something that they've talked about? Good. Some courses they go, there are assumptions, they're not part of this course, you can do them some other time. Okay, but this course obviously not. So your assumptions are that the relationship really is linear. And because if it really isn't linear, then your formula should have been different. Okay, that equation that we wrote of beta 0 plus beta 1x, if it was an exponential relationship, maybe we should have done beta 1 times beta 0 times e to the beta 1 times x. Okay, so there's all these different choices for how we should have done the formula. So if it's not linear, it wasn't a good idea. Number two, that the errors, those residuals, are normal. I don't know what order these are supposed to go in, but I'm just thinking them off the top of my head. So, yep, they are normal. The errors have the same spread for any x, which the fancy word for this is homoskedasticity. Sometimes spelt with a C in this spot. No one will care. Homo meaning same. Skedasticity is apparently something to do with spread. Never quite understood that bit, but okay. And lastly, and impossible to check, that there is that all of your individuals are independent of each other. Observations are independent. Okay, so we need ways of checking those to see if they're really okay. For future reference, outside this course, a lot of the time, it doesn't matter that much. It's only bad if it's really bad. Yeah. So, I'm going to take them in the reverse order. 4, can only check if you know the story. Of how the data was collected. And you almost never know that if you're the statistician or the engineer. If you are, if you created the experiment, you would know. One way that people do check it is that they actually don't just record the x's but record what order you created them in, and if the y's have a pattern depending on time, then there's not relation, then there's not independence. But that's not traditionally part of this course. Number 2 is to find the residuals, you do the regression, and get the vector of residuals and make a quantile plot. That's what you do in this course, isn't it? Okay. Some courses you just draw a histogram and go, yeah, it looks normal. And in some courses you will do the Shapiro-Wilk test. But this course, QQ plot. And if your QQ plot is roughly on a straight line, you're good. That is so not how you spell roughly. Roughly linear is good, badly not linear is not good. So badly not linear would be something like right. There'll be dots though, of course, so it'll always have a bit of a curve. You just want it to sort of, if you put your pencil over it, they're all under the pencil, that'll be okay. Jono Chuk would call it the fat pen test. So not this pencil, no, you get one of your one of your nice tri pencils for making it easy to hold pencils, and you stick that over it. So number 1 and 3. 1 and 3 are both answered with the same graph. You need to get the residuals as well for that, and you want to do a residual plot. Which has the x's here and the residuals here. Be careful in MATLAB, it has a strange order that I think you put the y first and then the x when you ask MATLAB to plot things, so make sure you keep track of that. And there should be like a 0 line in the middle, and you need to see 2 things. So for assumption number 1, you need to see random scatter on both sides of the line, so no particular pattern. So number 1, good is, well, no pattern for, above or below. That's good. So what you wouldn't want is it to do something like that. And number 3, same spread all the way along. So what you wouldn't want is for it to be fatter here and thinner here and fatter there. Another lecture I've sort of known as Jono again is to sort of cover up a little zone and move the zone along and just think about the total amount of spread in each zone, and if it's roughly the same as you go along, then that's what you're looking for. Or even cut it into 4 or 5 bits and just look to see if there's a lot of difference in that. And it really just looking at it going, yeah, it's not too bad. Okay, so when your lecturer asks you to check the assumptions, you need to say what graph you're looking at, what you observe, and what it means for each of them. Now, to be fair, that would be 12 marks, but it's usually only worth 4, 1 for each assumption. But you need to say which graph, what you see, and the conclusion. Okay, so you'll have 4 sentences, once for each assumption. You'll say, for linear relationship, I observed the residual plot and there was no pattern above or below the 0 line, and therefore the linearity assumption is appropriate. And for the normality, you might say, for the normality assumption, I observed the residual, the QQ plot, and I saw maybe not serious, significant deviation from the straight line, and so I conclude that the normality assumption isn't appropriate. Something like that. Most exams you just include they're all appropriate because they want you to be able to do it afterwards. Yeah. God, that'd be a really interesting exam to give you 2 of them and go, pick which one is appropriate and do that one. Oh. Wouldn't put it past some people. It sounds kind of cool, but it'd be a lot of work to set up, and most people don't want to do that much work just to write an exam. So sometimes the psychology of writing exams is a good thing to know because it helps you predict what might be in the exam. All right, so that's the whole of regression. Yeah. I can't give you much details about what you might see because never having done one, and you having a different lecturer every year for the past several years makes it a bit difficult to predict from the past exams what's going on. But you can say that most of your exam is likely to not be calculation but interpretation. To say, here is a thing you see, what do you see? And it's a little bit like they'll go, here are all these graphs, and they'll often chuck an ordinary scatter plot in there just to throw you off. And they'll say, check the assumptions. And so you say you have to look for the right graph. Or they'll give you various MATLAB output and you have to pick the one that corresponds to what you're looking for. So you'll need to look up in your MATLAB stuff that you did and remember what it was like looking for the information you needed so that you can see it even if you didn't make it yourself. Okay. Getting pretty tired, but I could do one more thing if people want to stick around for like half an hour. Sorry?
I'm done.
You're done, yeah. I'm done. Good. Probably tomorrow this will be ready and I'll email you all. And I'll put it on the website under whatever headings it goes under. I've had trouble cutting the videos apart recently, so it may all be in one video and I'll just tell you what time stamp the statistics starts. if you want to look for that. Thanks everybody. We're open all the way to the exam, to the end of the exam period. Also during the break, if God forbid you need to do a replacement exam, we're still around, but only in the afternoons during the second 2 weeks of the break. And as we get closer to the exam, it will get busier and busier in the Maths Learning Centre, and I will start to move second years next door so there's more room for first years. So I may declare a couple of extra tables nearby, but I'll also keep an eye out for you. If you're sitting around there nearby, feel free to run in and say, when you've got a moment, come and chat to us, and I'll come out eventually. Okay, good luck guys. One will be the imaginary part, one will be minus the other. Yeah. But that's okay because you're just going to multiply by a constant anyway. Yeah, sure. So I think it's okay. That's why I said a solution.
Because when I look in the solution, I'm pretty struggling with this too. I said why this one is only using the y1, not y2.
And it's because, well, I mean, the real part of y1 is the same. Yeah. Because they're conjugates of each other. And the imaginary parts are just negatives of each other. And so because you're going to put a c2 in front of it anyway, it's not going to make a difference.
So just
yeah,
sure. And also, so